Hey everyone, it's Dave here. We're live again with Chegg. Once again, I'm partnering with Chegg to bring you some live office hours. So all semester long on Tuesdays, I'm going to be going over some Organic Chemistry 1 tips for you, and we are taking questions. So feel free to ask questions. This, once again, is going to be every Tuesday, although I think starting next week, we're going to be doing this at 5 p.m. PST instead of right now, it's 4 p.m. PST where I am. So that will be a time change. But other than that, it looks like we're going to be doing this every Tuesday. Now, Chegg is covering other topics as well. So there's a little code up on the top left, the QR code there. So you can scan that and you can check out what other subjects they are doing these office hours for. And so there's a bunch of different topics. And so whatever courses you're in right now, these are meant to be helpful sessions for you guys. And so over here, I'm going to be keeping an eye on the chat. I have about a dozen questions ready to go. But once again, feel free to ask your questions in the chat. Last time, we did have quite a lot of activity of people not talking about Organic Chemistry 1. Again, please, saying hello is very nice, but a lot of people were asking a lot of questions that were not pertaining to Organic Chemistry 1. So please, if you can, try to limit the discourse to questions that are on topic here. Although, thank you. I appreciate being told I'm awesome. But anyway, so yeah, once again, we're doing Organic Chemistry 1. So let me go ahead and go over here to my to my prepared questions. So so last week we did a bunch of nomenclature and conformational analysis. So today I want to build on the conformational analysis and the nomenclature, and we're going to start to incorporate a bunch of and RNS and isomerism and that stuff. That's generally the second thing that happens in an OChem 1 course after those first few topics that I mentioned. So let's build upon what we did last week. So this first one says, draw R2-chlorohexane. So the first part is easy. 2-chlorohexane, we can just draw that as we already know from the IUPAC nomenclature. So hexane, hex means 6. So let's draw 1, 2, 3, 4, 5, 6 carbons. Once again, every endpoint and vertex is a carbon atom. And then we have on carbon 2, a chloro group. So it actually doesn't matter which side we start from because we get to determine that. So we're going to have a chlorine atom right here. So here is our carbon 2 right there. Now, the question is it going to be on a wedge bond or a dash bond? And this is an R stereocenter. It's telling us that we have an R stereocenter. So by the Kahn-Ingold-Prelog convention, the way that we determine RNS is that we write the priority of the 4 groups on this carbon. So let's go ahead and draw a wedge and a dash. So we know that one of these either the wedge or the dash is going to have the chlorine atom, and then the other one is going to have the implied hydrogen. So the question is which? Is the chlorine on the wedge or is it on the dash? So by Kahn-Ingold-Prelog convention, we're determining the priority of the groups by atomic number, going 1 atom at a time. So let's just go ahead and arbitrarily write this. And then if this is not correct, we can always switch it back. So this carbon is the chiral center, right? This carbon right here is attached to 4 different groups. Has a chloro group, a proton, this methyl, and then the rest of this carbon chain over here. So those are 4 different groups. It's an asymmetric carbon. It's a chiral center. It's a stereocenter. These are all ways of saying the same thing. So we're going to assign them. We're going to assign the group's priority according to atomic number. So chlorine is obviously priority 1. Chlorine is the heaviest, and then the hydrogen is obviously priority 4. Now, we have carbon, and those tie. And so the first very important thing that we need to understand is that we're not comparing the methyl group and this straight chain butyl group, right? We're comparing a carbon atom and a carbon atom. It's 1 atom at a time. So if the carbon atoms tie, we see what those are connected to. So this carbon is attached to hydrogen, 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 and then this carbon is attached to hydrogen, hydrogen, carbon. So It's as though two of the hydrogens cancel each other out, and then carbon beats hydrogen. And so because this carbon beats this hydrogen, this is going to be priority 2. And then that will mean that this direction is priority 3. Now, now once you have determined the priority of all the groups, you orient yourself so as to have the lowest priority group facing away from you. In this case, that's already here. The dash bond has the hydrogen. So remember, the dash bond is going away from us. It's farther away than the plane of the page or the screen. And so that's already away from us. And then we just go, we look and see which direction we're going. Here we're going clockwise to go from 1 to 2 to 3, and clockwise is R, right? R is clockwise. If we had gone counterclockwise, 1, 2, 3, the other way, that would be S. Okay, so it happens to be the case that we chose the correct configuration. If we wanted to draw S, the S isomer, we would put that on the dash bond. Whoops, not S, chlorine. And so this is the S isomer there. And so it gets a little trickier here when you have the lowest priority group facing you. So remember that the implied hydrogen would therefore be on the wedge bond. You can do a couple of things. You can either pretend that you're on the other side of the molecule, or equivalently, you could, in your mind, flip the molecule onto the other side. A lot of people have trouble with that kind of spatial reasoning. So another trick that you could use is just pretend that the lowest priority group is away, and then invert your answer. So here we would be saying 1, 2, 3. And so again, we would go like this. And so that's clockwise, and so it appears as though it would be R. But because we would have to invert that stereo center to get it the way we want it, we invert our answer. So looks like R is S. So that's all you do. That's an easy trick that I've taught my students in the past if you have a hard time kind of visualizing the molecule a different way. So that's the correct answer right there. Let me check the chat here. Let's see. Okay, cool. Pretty on topic, guys. Yes, Lance, we're going to stick to OChem 1 for the semester. By the end of the semester, we might be dipping into some OChem 2 topics, though, depending on how things go. Let's see. Oh, Soul Pen, we're going to wait a little bit for, I think maybe I'll hit some oxidation and reduction next week. This time I want to focus on these topics here. Let's see. Okay. So Jeremy says, how can you determine the major product of a given reaction based on the stability of the intermediate carbocation formed, and what factors influence that? So, so in that situation, you want to be aware of carbocation rearrangement, right? If you have a situation where there's a leaving group. So we're actually, the next couple of weeks, I'll probably be going over SN2, SN1, E1, E2. I'll spend a lot of time on that because that is a very big topic. But let's say you had, a leaving group that, well, maybe it wouldn't. Yeah, let's say on a secondary carbon, if this were to leave and you were left with a secondary carbocation, you would undergo carbocation rearrangement. You would get a hydride or a methanide shift, in this case, a hydride shift. That would shift over and rearrange to give the tertiary carbocation. So whatever the most favorable carbocation intermediate is that you can get, that will be the intermediate from which we proceed to the product. Okay. JA says, what if hydrogen is given on a wedge? Do you flip the absolute configuration? Yes, absolutely. So that's what we said here. If we had the chlorine on the dash and the hydrogen on the wedge, then that would violate the conditions for assigning R and S, because we need the lowest priority group away from us, but we can just pretend that it's away from us. So the thing is that switching any two groups on a chiral center inverts that chiral center. So we can take the chlorine and the hydrogen and pretend they're the other way, assign R, and then simply invert our answer, right? So we're flipping it to assign it, and then just flip your answer to get S. And so if chlorine is on the dash, In this case, it would be the S configuration. Okay, let's see. JAMA MAMA, only if there are 4 unique ligands bound to the carbon. If it's 2 hydrogens, there's no R or S because they're the same. That is correct. So if you have 2 of the exact same group on a carbon, it cannot be a chiral center. We need 4 different groups to get a stereocenter. If Rihan says, if I chose to do it on the right-hand side of the carbons, would it still be a wedge? Oh, I see what you're saying. So if we went boom, 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 and then we did this one over here, yes, absolutely, this would still be R because we're saying priority 1, priority 2, priority 3, and that is still clockwise. So yes, and you'll notice that that is actually just if you flip it 180 degrees in the plane of the page or the screen, that's the same molecule. So absolutely, that would be the same and still R. If hydrogen on a wedge. Yes, JJ Thor, exactly correct. If the hydrogen is on the wedge coming towards you, you can just flip them and then invert your answer. Fire King M101, SN2, do we have to worry about stereochemistry? Yes, and once again, probably next week, I will devote most of the time to SN1, SN2, E1, E2. SN2 is a stereo-specific reaction. You will always achieve an inversion of chirality, so that is very important for that reaction, and we'll talk about it a ton next time. Okay, all caught up. So let's head to number 2. So I am going to do mostly the chirality and isomerism stuff, but let's also talk a little bit about acid-base, because acid-base reactions, that is one of those things that should be well understood from Gen Chem, but sometimes doesn't always make it. And then in organic chemistry, it's extremely important. We have a lot of acid-base reactions in organic chemistry. So let's look at this one. Ethanoic acid and ammonia undergo an acid-base reaction. Draw the conjugate acid and conjugate base, and then state which is the preferred direction of the resulting equilibrium. So a little bit of nomenclature mixed up in here too. Ethanoic acid, we know that that's a carboxylic acid, and because of eth, we know that it is a 2-carbon carboxylic acid. So there is that. And then ammonia obviously is NH3. And so we're going to have an equilibrium here with the conjugate acid and base. So ethanoic acid is obviously acting as the acid. So what is the conjugate base? That is going to be here, the ethanoate ion there. And then that means that ammonia got the proton. So we have the ammonium ion NH4+. So certainly this, so this is going, so we have, let's label these for clarity. We have the acid and we have the base and we have the conjugate base and the conjugate acid. So it's very important to understand that the acid becomes its conjugate base, because the conjugate base, this anion, oxyanion, could get a proton and go back to being the acid, right? If it loses a proton, it's behaving as an acid. If it gets that proton back, it's behaving as a base, conjugate base. And then ammonium, so ammonia acts as the base. And then if it gets a proton, it will become its conjugate acid, the ammonium ion. So which direction is going to be preferred in this equilibrium? So pKa is just for reference. For a carboxylic acid, a standard carboxylic acid like this, pKa is going to be around 5. And then the ammonium ion is pKa around 9. Remember that the lower the pKa, the more acidic, the thing that we're talking about here. And so that means that ethanoic acid is a stronger acid than the ammonium ion. So and by 4 orders of magnitude. So it's 10,000 times more acidic. So the equilibrium, the side of the equilibrium that is favored is going to be the side with the weaker acid. So this is the side that's going to be preferred because it is a weaker acid, so it has less impetus to react. right? If this carboxylic acid is much more likely to behave as an acid, then it's much less likely that the conjugate base will go back to being the acid. This is a very stable conjugate base. This oxyanion is stabilized by resonance, right? That's why this is so much more acidic. This is why carboxylic acid is so much more acidic than an alcohol. It's because of the resonance stabilization on the conjugate base. And so ammonium is a weaker acid, so it's less likely to react, which means the equilibrium is going to stay on that side. So this will be the side that is favored on the resulting equilibrium, which means the right arrow, the one on the top pointing to the right, that is going to indicate the preferred direction of the equilibrium. Okay, let's take a look, see what I missed. Okay. Jamma Mamma, yeah, I know it's acetic acid. Just ethanoic is IUPAC. So last week we were talking about IUPAC nomenclature, so it's good to build on that. So we want to be able to use IUPAC rules to name carboxylic acids, esters, aldehydes, ketones, etc. But yes, of course, that is acetic acid. Let's see. Okay, all caught up. All right, so one more before going back to the isomerism stuff. Which is the most stable? We have cyclopropane, we have cyclobutane, we have cyclopentane, and we have cyclohexane. So if we're talking about the stability of these cycloalkanes, we're definitely going to be looking at ring strain. So these much smaller rings have a lot of ring strain. We know that a triangle, an equilateral triangle like this has 60-degree bond angles. A square has 90-degree bond angles, right? So we know that these are all supposed to be sp3 carbons. These are all fully saturated molecules here. There's no double bonds, right? These are supposed to be all sp3 hybridized carbons. They all have 2 hydrogens on them. So they want to have 109.5 degree, 109.5 degree bond angles. That is the desired geometry around an sp3 center. And the one that does it the best is cyclohexane, right? Cyclohexane has it's every single, right? If you draw the chair, if you draw a chair conformation, we are seeing that. And then if you, let's put 2 of the hydrogens there, it's kind of like you can sort of see the tetrahedron at each carbon, right? You kind of have to use your imagination a little bit, but each of these carbons is exhibiting perfect 109.5 degree bond angles, perfect tetrahedral geometry. So there is no ring strain. There is tremendous ring strain on cyclopropane, and then quite a bit with cyclobutane as well. And so that, and then also with a chair, there's all staggered configurations, right? All of the carbon, all of the carbons are anti to one another. So there's a multitude of reasons. Sterics and then also ring strain would be the main one. And then we have a lot of evidence for this in terms of heat of combustion. If we take the heat of combustion per CH2 unit, we can look at the amount of energy that's released if we kind of take apart these molecules, and we can see that the cyclohexane is definitely at the lowest energy of the molecules. So we're going to go with cyclohexane. That's the most stable. All right, let's see. Okay. Okay. Now let's go over here. Okay, so back to some isomerism stuff. If a compound possesses one or more chiral centers, the compound may be chiral, will always be chiral, or will never be chiral. So we're talking about one or more chiral centers. So what does that mean? All right, let's say we have one chiral center. if we have one chiral center, let's just say it's this 2-bromobutane, then this must be chiral, right? We have, if a molecule has one chiral center, then it must be chiral. It will have this plus enantiomer, right? The enantiomer is the mirror image. So if you take this, if you put the bromine on the dash bond instead of the wedge, you'll get the mirror image. The mirror image is called the enantiomer. And so one chiral center, you must have it will be chiral. Now, what if we have two chiral centers? So let's say we have something like this. Now, this is actually a meso compound. There's an internal plane of symmetry. So there are two chiral centers here. There are two. These are each chiral centers because from the perspective of this carbon, there's four different groups: the bromine, the implied hydrogen, this way around the ring, and this way around the ring, which are different because if you go this way, you hit that bromine. If you go this way, you don't. So these are two chiral centers. However, the molecule is achiral overall because of the internal plane of symmetry. And we can prove this to ourselves, right? If it's achiral, then it's not different from its mirror image. So let's pretend there's a mirror plane here, and let's draw the mirror image, right? So if we're reflecting this across the mirror, well, look at that. We just got the same molecule again, right? And so you can reflect it across the mirror plane, or you can recognize that there's an internal plane of symmetry. However you want to rationalize it, this molecule is not different from its mirror image. Therefore, it can't be chiral. If something is chiral, it is different from its mirror image, right? Like our hands are chiral, right? We can't perfectly superimpose one over the other and have everything lined up. Not like this, right? But like this. So our hands are mirror images of each other. So there's an element of chirality there. So this has two chiral centers, but it is achiral. Now, that's not always going to be the case, right? If we had, if these were two different groups, if we have bromine and then chlorine, well, now all of a sudden, these are two different groups. That's not identical to its mirror image, right? These are two different groups. Furthermore, if we had one of these bromines, if they were both bromines, but one of them was on a dash and the other was on a wedge, now also it's no longer equivalent to its mirror image. So there's a situation where you have two chiral centers and it's chiral. So this question is a little bit tricky because it says one or more, right? And what we need to understand is if there is one chiral center, it must be chiral. If there are two or more chiral centers, it may or may not be chiral, depending on elements of internal symmetry. So if you have two or more chiral centers, you got to check, is there a plane of symmetry? Is it a meso compound? There's another thing we'll look at later called an inversion center. If we have time, it's towards the end. So if there's internal symmetry, it may not be chiral, but it can be, right? So the thing we want to understand is that the answer is that it may be chiral. We're not sure if it is or is not chiral. We have to investigate on a case-by-case basis. So let's see here. Okay. I think someone asked, yeah. Sorry, where did it go? Olaf Adams says, can you explain how you identify the chiral centers? Absolutely. So once again, for example, on this molecule here, we know that this carbon is a chiral center because it's attached to four different groups, right? So this bromine is one group. The implied hydrogen is another group. And then this carbon is a part of a methyl group. And then this carbon is part of an ethyl group. So those are two different kinds of carbon chains. And so it has to be an sp3 carbon, right? sp2 carbons and sp carbons are not going to be chiral centers. Those are carbons that are participating in double bonds or triple bonds. So that's it. We need four different groups, and that's it. So here that qualifies. Now, if we took away one of these carbons, whoops, that went all the way away. So let's say we had two identical methyl groups. That doesn't work now, right? if any two groups are identical, doesn't matter if it's two hydrogens, two methyls, whatever it is, it's not going to be a chiral center. Let's see. So hopefully that helps. Let's see. Yes, Cat Sperm says chiral center has sp3 hybridization and 4 different groups attached. That is correct. Yeah, there's a lot of weird comments here. Whoever's moderating, feel free to ban anyone with the profanity and stuff like that. Let's see. Okay. Okay, that's enough there. Okay, so going on to this one, identify every chiral center in this molecule and assign R and S absolute configuration. So this is great. This is what we just talked about. We've got 4 carbons in this molecule. So how many of these are chiral centers? This one over here is an sp2 carbon, so that doesn't work, right? This is attached. It has 2 bonds to the same oxygen atom, so that's not going to help. This one works though. We've got 4 different groups: the hydroxyl, the implied hydrogen, and then 2 different directions of the molecule, which is not symmetrical. This one also is a chiral center. So that's going to be has 4 groups as well. Over here, it's not though. This carbon right here has 2 hydrogens. So if it has 2 of the same group, that's not a chiral center. So we have 2 chiral centers. Now we want to assign R and S to these groups here. So let's start with this one over here. This is going to be priority 1. And the implied hydrogen here, let's just draw those in because that does help a bit here. And we know that the implied hydrogen is going to be carbon 4. Priority 4. Now, this is where Conning-Gold Prelog gets a little bit tricky. We have 2 identical carbon atoms. So remember, we're going 1 atom at a time. Carbon and carbon, identical carbon atoms, identical atomic number. That's a tie. So we need to see what those carbon atoms are attached to. So this carbon is attached to oxygen, oxygen, hydrogen. Right? We have this implied hydrogen right here. And then with Conning-Gold Prelog, if we have multiple bonds to the same atom, we count that group that many times. So if we have 2 bonds to oxygen, it's like we're counting oxygen twice. It's exactly the same as if that oxygen was bound to 2 different oxygen atoms. Okay, so oxygen, oxygen, hydrogen. This carbon over here is attached to oxygen, carbon, hydrogen. Right? We've got this oxygen in the hydroxyl, this carbon over here, and then the implied hydrogen. Sorry if that's a little messy. That's a dash bond to a hydrogen. It's getting a little crammed in there. So it's like the oxygens cancel and the hydrogens cancel, and then we're comparing oxygen and carbon. And oxygen has a higher atomic number than carbon, so that direction wins. So that's what we mean when we say we're going 1 atom at a time. If we have a tie, then we have to see what those atoms are connected to. So it can get a little complicated for long chains. So here is priority 2, and here is priority 3. We are going. We're lucky here that the implied hydrogen is already away from us, so we are in the correct vantage point to assign R and S. This is going clockwise, so this one is R. This is an R stereocenter right there. Okay, let me just get rid of some of this so we have a little bit of room. Yeah, let's get rid of the priorities. That will make it a little easier to get this other one. Okay, so there's the implied hydrogen. Okay, now, so we assigned this one, it is R. Now let's do this direction. So we are going to say that the oxygen is highest priority. That's the highest atomic number. And we're going to say that, again, hydrogen is the lowest priority. Now, once again, we have 2 carbons, 2 identical carbons. Those are going to tie. And so we have to see what those are connected to. So this carbon is attached to oxygen, hydrogen, hydrogen. This carbon is attached to oxygen, carbon, hydrogen, right? So this one over here, it's the oxygen in the hydroxyl and then 2 implied hydrogens. This carbon is attached to this oxygen in the hydroxyl, this carbon atom, and this implied hydrogen. So once again, we kind of are comparing and canceling out. Oxygens cancel out. One of the hydrogens cancels out. And so we are comparing carbon to hydrogen. Carbon wins over hydrogen, right? And so that means that we're going to label this priority 2. Let me do that in pink. And actually, let me erase this one. That might get a little confusing. So in pink, we're saying this is priority 2, and this is priority 3. So we are going counterclockwise now, right? Again, the hydrogen is the furthest away from us, so we're in the correct vantage point. And to go from 1 to 2 to 3, we are tracing counterclockwise, so that is S. Okay, so we have 2 chiral centers. This one is R, this one is S, and that's about as complicated as it usually gets with R and S. We have a couple different chiral centers. We found some carbons that tied. We had to go to the next set of atoms. As long as you can do that, you should be okay. And then an interesting thing, once again, if the hydroxyl was on the dash and the hydrogen was on the wedge, we could just arbitrarily swap them and then assign R and S and then just invert our answer, right? So if you invert it to see what it is and then you invert your answer, that's fine because you're inverting it once and then again back to the original. So that is the best tip there. Okay, let's see if I missed anything. Let's see. All right, this privacy guy, if we can please block him, that would be great. Okay, yeah, imperfect mammal. Can you do MO theory on conjugate systems? I definitely can. I probably will. I would need to prepare that because it's very visual heavy. So I will definitely include that when we do Diels-Alder. I will do that because there's a lot of MO stuff for Diels-Alder. So I will make a note of that for a future session. Rehan says, just to check my understanding, though there are 2 chiral centers, this is not achiral. If you're talking about this question that we just did, you are correct. It is not achiral. It is chiral. So achiral means not chiral. So we have 2 chiral centers here. There is no internal symmetry. If this hydroxyl were a carbonyl, then actually that would be a different story because then we would have internal symmetry potentially. Actually, no, even then it wouldn't be because if you rotate this, no, it still would be chiral actually. But so there's ways for it to end up being achiral, but this molecule as drawn is chiral. Okay. Let's see. Okay, let's go to the next one. Okay, draw all of the possible stereoisomers of 2-bromo-3-chlorobutane and state their relationship. So we want to talk about enantiomers and diastereomers. So let's draw all of them first, and then we'll get the relationships. So we have got, so it's a butane and then 2-bromo-3-chloro. So let's just draw one of the possibilities. We have to draw all of them. So let's just draw one of them to start. So here's carbon 2. And I'm going to put that bromo group on the wedge. And then we have 3-chloro. So let's go ahead and put that chloro group on the wedge. So what else can we have, right? We've got them each on wedges. So what if they're both on dashes? Let's put them both on dashes. That would be another possibility. Now, what if we have one on a wedge and one on a dash? We can have that too, right? So let's have the bromo group on that wedge, and then let's have a chloro group on the dash, and then let's get the other one. Let's put the bromo group on the dash and the chloro group on the wedge. So that's all. Those are all the possibilities. Those are all the possible permutations of these 2 chiral centers. And we know that that's true because the number of stereoisomers that are possible is always going to be 2 to the n, where n is the number of chiral centers. So if there are 2 chiral centers, the number of possible stereoisomers is 2 squared. 2 squared equals 4. Those are the 4. If you have a molecule with 3 chiral centers, 2 cubed is 8. You can have 8 stereoisomers, and then 16 at 32, etc. So you can get a lot of stereoisomers if you have 4, 5, 6 chiral centers on the molecule. Here we have only 2, so the maximum is 4. We have 4 stereoisomers. So those are the ones that they are. What are their relationships? So we want to talk about enantiomers. Enantiomers are mirror images of one another, but another way of thinking about them is that if you take a molecule and you invert every one of its chiral centers, you get its enantiomer. So these are enantiomers, right? These are both on wedges. Now they're both on dashes. We have inverted each stereocenter. So these are enantiomers. Likewise here, these are enantiomers. Okay, and now let's use a different color here. These are diastereomers. These are diastereomers. These are diastereomers. And these are diastereomers. So what are diastereomers? Diastereomers are stereoisomers that are not enantiomers. Okay, so if you invert every single chiral center on a molecule, you get its enantiomer. If you invert one or more, but not all of the chiral centers, so basically any other possibility except for inverting all of the chiral centers, you get a diastereomer. So here in this direction, we inverted one of them. In this direction, we inverted one of them, the bromine. In this direction, we inverted one of them, the chlorine. In this direction, we inverted one of them, the chlorine. So when you have 2 chiral centers, if you invert one but not both, you get a diastereomer. Only if you invert both of them do you get an enantiomer. So what we have to understand is that if you have a chiral molecule with many chiral centers, there will be many, many, many diastereomers, but only one enantiomer. A molecule can only have one enantiomer. That is its mirror image, but it can have many diastereomers. So for example, if something has 3 chiral centers, there are 8 possible stereoisomers. So if you take any one of those possible stereoisomers, you've got 7 remaining. Only one of them will be its enantiomer. The other 6 will be diastereomers of that original example. So there are all these different relationships. You can take any stereoisomer and then talk about its enantiomer or multiple possible diastereomers. So hopefully that is clear. This is a very simple example that is very, very good for understanding, right? We really need to understand what enantiomers are, what diastereomers are, and to be able to identify that relationship between 2 stereoisomers. Okay, so let's see. What did I miss? Okay, let's go forward from there. Cat Sperm says, wait, if both are on the wedge or both are on the dash, aren't they the same? It would be if they were the same group, but they are not the same group. It's a bromine and a chlorine. If they were 2 bromines, then yes, it would be the same molecule. And yeah, Sammy Douglas says, but aren't some of those the same? No, these are all different. These are all different isomers. Once again, if there are 2 chiral centers, there will be 4 stereoisomers. Those are the 4 stereoisomers. Yain Malik asks, maybe a dumb question, but how did you immediately know that you had to draw these 3D lines, or is that not necessary? So yes, it absolutely is necessary. So these are sp3 carbons, right? If these are sp3 carbons, there's 4 bonds, and sp3 carbons obey tetrahedral geometry, 109.5 degree bond angles. So that means that you have to have a group on a dash and a group on a wedge. And so there's going to be implied hydrogens. So with organic chemistry, with the line notation, we definitely, right off the bat, we have to be very comfortable looking at molecules in line notation, seeing where the implied hydrogens are, understanding what the geometry is on each of the atoms, and so forth. Let's see. Okay, globulic. But what if you have meso compound? Then this formula is not accurate. So you can still have different stereoisomers, right? If you have, like, for example, the meso compound we did earlier with the cyclohexane and two bromines, you can have a diastereomer that will be chiral. If you take one, they're both on the dash, or if they're both on the wedge, but you put one of them on the dash, that's no longer meso. So meso is a term that will apply to only one or some of the possible stereoisomers. We still will have other stereoisomers for that formula that will be chiral. Izyane again, I heard many people having difficulties with recognizing SN1 and SN2 and E1 and E2. Yes, absolutely. That's one of the very, very most popular areas that organic chemistry students need help with. So I guess I will probably go ahead and I tell you what, I'll start covering that next week, and I'll sprinkle in other topics as well, but I will make sure to be covering some questions on those mechanisms for probably the next 2 or 3 weeks, because everybody's kind of hitting those first mechanisms at different times, but it is probably the single most important thing to start wrapping your head around in OChem 1, because it's really the foundation for mechanisms, which is just the rest of what you learn in OChem, more or less. So we will talk a lot about that. Let's see. Yes, if both groups were chloro, would there be few? Yeah, so that would be meso. And so no, there would be the same number of stereoisomers. It would still be 4 stereoisomers. It's just that not all of them would be chiral, right? So that's an important distinction. If there are 2 chiral centers, the only time it wouldn't apply is if they're not actually chiral centers because of the symmetry. So then that would be the case. Okay, almost caught up. Okay. Now, okay, so let's combine this with the chair stuff that we were doing. So we're going to want to assign R and S to each of the stereocenters in the molecule, and then draw the molecule in its most stable chair configuration. So we have 3 chiral centers, right? We've got this one, we've got this one, we've got this one. So let's do these one at a time. Up here, we've got chlorine is the highest priority, hydrogen is the lowest priority. And then, so a quick trick here, right? If on the right, we have no substituents, on the left, we have substituents that have higher atomic number than carbon. We're just going to go ahead and say that this direction is priority 2, and this is priority 3. Okay, so 1, 2, 3, we're going clockwise. This one is R. Let's put that here. Okay, now let's erase the priorities, because this will get very messy very fast if we don't. Now let's go to this one. So fluorine will be priority 1. Hydrogen will be priority 4. Now, in this case, we have a ring, so it's a little easier. But on the linear molecules, don't forget that it's not always substituents on the dash and wedge that are going to be priorities 1 and 4. Sometimes the carbons in the chain can be the highest priority or the lowest priority or whatever it is, especially if there's no hydrogens, right? Sometimes a carbon will be connected to 3 other carbons. So then you really have to be careful and see which direction is the highest priority. Now here, this carbon is connected to a bromine. This carbon is connected to only the heaviest would be the carbon. So we're going to go this way for 2, and we're going to go this way for 3. Now, so here's a situation where we have the lowest priority group not away from us, but actually towards us. Okay, so, oh, wait, you know what? Did I make a, oh, shoot, I made an error over here. This is going to be 1, 2. Yeah, we said that this was like this. So that will be S. Sorry, someone caught that. Okay, so back to this one here. We have the lowest priority group away towards us. So the simplest thing here is just pretend that fluorine is towards us. Okay, so we're going 1 to 2 to 3. So that looks like it would be S, but then we invert our answer and it is R. Okay, so we are saying that we're pretending fluorine is on the wedge. If fluorine was on the wedge, we would be going counterclockwise. So invert your answer. And from S, it is actually R. So that's the way you do that one. Okay, finally, we have this guy. So we've got the highest priority group is bromine, lowest priority group is hydrogen. And then once again, we've got fluorine on that carbon and no substituent over here. So that is going to be like that. And once again, we have the lowest priority group towards us. So we can invert that arbitrarily and then invert our answer. So this looks like it is going clockwise. So it should be R, but we invert our answer. And so that is actually going to be S. So we've got SRS. Now it is asking us to draw the chair. So let's go ahead and draw the chair. Let's draw a chair like this. Now we can number this however we want. So I'm going to arbitrarily number this like this. And this is not IUPAC nomenclature, or this is not IUPAC numbering. This is just bookkeeping for me to know what I want to do with the chair. So let's just pick a carbon to be carbon 1 and then go either clockwise or counterclockwise. So I'm saying that this is carbon 1 and we've got chlorine up. Now, if we go around to carbon 4, we've got bromine down. Right? If the wedge is up, so this has to be the equatorial position, right? In fact, why don't we just go ahead and draw all of the bond angles? So those are all the places that substituents can go. On where I've designated carbon 1, we've got chlorine up. On this carbon, up is an equatorial position, right? We're not going to have this go straight up. Remember, we want to be able to kind of visualize the tetrahedral configuration at every carbon. So that is going to go up equatorial. On 4, we've got bromine down. It's got to go down. And on this carbon, the down direction is equatorial. And then go one more on carbon 5. We have fluorine going down. So let's put the fluorine there. So this does happen to be the most stable chair configuration. How do we know that? That's because we have two groups that are equatorial. The chlorine is equatorial. The bromine is equatorial. The fluorine is axial. Equatorial is more energetically favorable position than axial because the axial groups participate in those diaxial interactions. So there's other hydrogens here. There's a steric hindrance. There's a repulsion that's associated with that axial position. So the more groups that are equatorial, the better. And furthermore, bromine and chlorine are bigger than fluorine. So there's actually a higher energetic premium on having the larger halogens be equatorial because they've got a larger electron cloud. So there's going to be more repulsion. So this is the best chair conformation for that molecule. Okay. There is, I assume, Raichiro caught my error on the first S1. Yes, a couple people caught that. Sorry about that. Sometimes you have a little brain fart. Yep, 3 people got it, 4 people got it. Okay. Let's see. Arbitrarily. That's a funny joke. And that's it. Okay, so let's go back over here. Consider the following molecule. So this is a good one. Once again, very, very important that we understand what enantiomers are, what diastereomers are, how to identify them, how to draw them if prompted. So here we have this molecule. We want to draw its enantiomer. So a couple ways we can do this. You can either imagine a mirror plane and flip this over the mirror, right? You draw the mirror image. But honestly, it's quite a bit easier to just invert every stereocenter. So just draw the same molecule. We've got a, what functional group is this? We've got an ester, right? That we need to know. And now we're going to invert every stereocenter. So here we have a methyl on a dash. So let's put the methyl on the wedge. Now we've got the hydroxyl on the wedge. So let's put the hydroxyl on the dash. That's the enantiomer. all you have to do is invert every stereocenter, and you will get the enantiomer of the molecule. Now, if you want to get a diastereomer, so notice I said a diastereomer because there are two. So if you have two chiral centers, if you invert one chiral center but not both, you will get one of the two possible diastereomers. So let's pick one. Let's draw, let's put it over here so we have a little more room. So let's say that we're going to put the methyl on the wedge, right? The methyl was on the dash, so let's put it on the wedge, but then we have to leave the hydroxyl on the wedge, right? If we also invert the chiral center with the hydroxyl, then you're getting the enantiomer. We want to invert one chiral center, not both. So that would be one possible diastereomer. The other possible diastereomer would be if both of them were on dash bonds. So that would be that. Okay, now we have a structural isomer. So a structural isomer is the same molecular formula, so the same number of atoms of the same elements, but differing in connectivity. So stereoisomers are not different structural isomers. Stereoisomers have the same molecular formula and the same connectivity. Right, it's a narrower type of isomer. So this molecule and the enantiomer and the diastereomers, they have the same connectivity, the same atoms connected in the same way, but they differ in the way they are distributed in three-dimensional space. That's what a stereoisomer is. A structural isomer, we have different connectivity. So the easiest way to do this is just take a functional group, pluck it off, and put it somewhere else. That's honestly the easiest way to do it. So just looking at this, there are so many different structural isomers that you could put. I'm just arbitrarily going to say, let's do this, and I'm going to leave the methyl group there, and then I'm going to take this hydroxyl, and I'm going to move it over here. That's what I'm going to do. That's it. I took the hydroxyl, I snapped it off, and I put it somewhere else. So that's a different structural isomer because there's different connectivity. They're not connected in the same way as the original molecule. So that's a structural isomer. And then let's do a conformational isomer. So a conformational isomer is where, remember when we were doing Newman projections, if you start rotating carbon-carbon sigma bonds, you're going to get different conformations. So we can identify any carbon-carbon sigma bond, spin it, and then spin, move whatever groups are affected by that spinning, and we will get a different conformation. So I say I want to spin this bond. I'm going to spin this one, and I'm going to spin it 180 degrees. So I will get this part of the molecule didn't change, and I've got this one here, and then I've got this carbon here. And so now I'm going to have this methyl group or this ethyl group going up like that. And I've got this methyl group over here. And sorry, I forgot to write OH on the hydroxyl group there. So that's what happens when we spun this carbon, or when we spun that sigma bond 180 degrees. So it's like we took this portion of the molecule and flipped it over, right? So it's the same molecule. It's the same, structurally not any different, stereoisomerically not any different, but we've spun one of the bonds to get a different conformation. So that's a different conformational isomer. Okay. Globilic said, I think based on the last question, is asking they can't all be axial. No, they cannot all be axial. They cannot all be equatorial. So once again, we're here. If that's carbon 1, this is going up. The up bond here is necessarily equatorial. The down bond here is necessarily equatorial. The down bond here is necessarily axial. So we are not determining axial and equatorial, right? This is what it is. And then we could flip the chair. We could flip the chair and then everything equatorial would become axial and everything axial would become equatorial. So if we flipped it, the chlorine and the bromine would be axial, but the fluorine would be equatorial. And so that would be the less stable because we'd have two axials, but we cannot just arbitrarily say they're all axial, all equatorial, etc. The way the chair structure works tells you whether a group is equatorial or axial. Sammy Douglas asks, is it possible to have diastereomers with only one chiral center? No, it is not, right? If you have one chiral center and you invert that stereocenter, you get the enantiomer. There's only one chiral center, so there's only two. So remember, 2 to the n, 2 to the 1 is 2. There are 2 stereoisomers, and they're an enantiomeric pair. That's it. That's all you get. Okay. Kevin asks, wait, isn't that a constitutional isomer? Yes, structural isomer and constitutional isomer are completely synonymous. They mean exactly the same thing. Pounch asks, a conformational isomer is basically the same molecule. Yes, absolutely. It's 2 different conformations of the exact same molecule. So stereoisomers are different molecules, right? Enantiomers are different molecules, but different conformations are of the same molecule. We're just spinning bonds, right? So it's the same molecule. Sakya asks, how do we know which conformational isomer is more stable? So you would be looking at, you can draw Newman projections for a particular bond. So you would talk about the stability surrounding a particular sigma bond, and then you would just be looking at whether it's staggered or eclipsed, if you have gauche interactions, etc. We did some Newman projections last week. I can try to include one next week if you like. Sammy asked the same question again. No, yeah, diastereomers, you need 2 chiral centers. Let's see. That's it. Okay. Oh, yeah, Ryu Chiro says, can we have an achiral diastereomer? Absolutely, right? You can have one of the stereoisomers be meso, and then it would not, that isomer would be achiral. But then you flip one of them, all of a sudden you have a different stereoisomer that is chiral. Do we have time for one more? Yeah, okay, let's do one more real quick. I can include these next week if we need to. So what is the hybridization of the 2 oxygens in this? So I've given you a condensed formula notation. So let's convert it into line notation. We have H3C, that's a methyl. Then we have a CH2. And then we have CO2. So when you have CO2 right in the middle of the molecule there, that's not carbon dioxide, right? That means we have C, and then that invariable means we have a double bond to one oxygen and then a single bond to another oxygen. So here's H3C, here's CH2, here's CO2, and then we have CH2 and then CH3. So what are the hybridizations of these 2 oxygens? We had a couple of questions earlier on hybridization. So how many groups are how many electron domains, I should say, are surrounding each of these oxygens? And so over here we have 1, 2, 3. Lone pairs count as electron domains, right? So 1 lone pair, a second lone pair, and 1 carbon atom. We have an sp2 hybridized oxygen that is going to exhibit trigonal planar geometry. So roughly 120-degree bond angle. It's not exactly, because the lone pairs make it slightly different, but it's roughly trigonal planar. And again, that's because there are 3 electron domains. So we need 1 s orbital and 2 p orbitals to make sp2 hybrid atomic orbitals to accommodate those 3 electron domains. Then over here, we have 1 electron domain, 2 electron domains, 3 electron domains, 4 electron domains. So 4 electron domains is going to be sp3 hybridized. We're accommodating 4. We have 2 lone pairs, 2 carbon atoms. So we need an s orbital and 3 p orbitals in order to get the sp3 hybridized atomic orbitals to accommodate these 4 electron domains. So we have sp2 and sp3. That's very important. We need to be able to do this with carbon. We need to be able to do this with oxygen and with nitrogen. That's about it. Usually just those 3 is going to be really important to know the hybridization. Let's just make sure in the last minute or so that I didn't miss anything. What if you have a E or Z that doesn't change and one chiral center? Yeah, you can have so the carbons participating in the double bond would not be the chiral center. I'll throw one of those in next time. But yeah, that's Konnengold Prelog. Yeah. Okay. So that's it. That's today's office hour. So again, today we focused a lot on stereoisomerism, different kinds of isomerism, building on conformational analysis and nomenclature. Next week, I may put a few more of these in, but I'll start to bring in some of the mechanisms, SN1, SN2, E1, E2, because that's definitely a major topic. So thanks everyone for for joining. Next week, it's actually going to start at 5 p.m. PST. So Pacific time, 5 p.m., which is an hour later than we started today. So take note of that. And I hope to see you next week.